today is given by Roberto Ribeiro Jr. Roberto completed his PhD in 2014 at IMPA, National Institute of Pure Applied Mathematics in Brazil. He conducted a postdoctoral research at University of Bath in UK, and currently he has a permanent position at Federal University of Paraná, Brazil. And his talk today is going to be trapped waves and collisions. Thank you, Roberto.
Okay, thank you, Adriana, for the introduction. And before I start, I would like to thank Davi Andrade for inviting me to give this talk, and all members of the organizing committee for this opportunity to present my work. And I would like also to thank the next speaker, Rafael, I think, for accept change his time with me. Okay, in this talk, I'm going to discuss about trapped waves. So first, I'd like to define or roughly define what are this kind of waves. So trapped waves are waves that, let's do this, are waves that remain trapped in a certain region of the space. Oops, I don't know why I cannot go on with the, okay, now, okay. In this talk, I will consider two cases of trapped waves. Case one, when we have a wave that remains trapped between two bumps. This is ongoing work in collaboration with Marcelo Flammarion from Universidade Federal Rural de Pernambuco, in Brazil, and Paul Milewski from University of Bath, UK. And the case number two that I'm going to talk is when we have a wave that remains trapped in a low pressure region. For this case, because of the time, I will give just some brief comments. Okay, let's start. Case one. So this case, the results that I'm going to present about this case are available in this paper here, which is in the archive. Okay, so first let's describe our physical problem. Let me give some description about the physical of our problem. So basically, we assume that at the free surface we have a wave, which is given by which is denoted by the letter zeta, and beneath of the free surface, we have a constant current whose intensity is given by the letter U0, and at the bottom we have a topograph whose shape is like described here. We have two bumps, and we denote the shape of the topograph, the profile of the topograph by hx. As is well known in the water wave community, the basic equation, the basic governing equations for the dynamic of a water wave are the Euler equations. We denote by U and V the components of the velocity field, and so the dynamic of the free surface is given as a solution of this nonlinear PDE that are the Euler equations. Here, P denotes the pressure, who is the density of the water, G is the gravity, and to solve this equation, we have to solve this equation in the fluid body, and we have also to deal with two boundary conditions, one on the bottom, this one here, and this system of the bound, this system of condition that evaluate along at the free surface. Basically, this equation here says that along the free surface, the pressure is equal to atmospheric pressure. Okay, I reckon that everyone here agree with me that this equation is very ugly, it's very hard to solve, because we have a system of nonlinear PDEs with free boundary conditions. So one approach used to study the dynamic of the free surface is trying to deduce some kind of reduce the models. For this purpose, we do the following. We make some change of variables, like it showed here, and after persuade some manipulation, we obtain that the governing equations, that the oil equations, that are the oil equations, are given in terms of three parameters: the parameter epsilon, mu, and f. The parameter epsilon controls the nonlinearity of the problem. The parameter mu control the dissipation of the wave, and f is the fluid number, which is the relation between the intensity of the current and the speed of waves in the long water wave regime. Okay. Besides this hypothesis of this non-dimensionalization, we also assume that the f, the fluid number, is given as it showed here. We consider that the fluid number is just a perturbation as the fluid number 1. By doing that, we try to establish some kind of balance among nonlinearity, dispersive effects, and topography effects. We also assume that the parameter epsilon is the same order of mu square, and plug all this assumption in the governing equations and truncate the equations, all the equations in order 1, we obtain this equation here for the dynamic of the free surface. This equation is known as the forced Cordovag-de Vries equation. Observe that when h, the topograph, is equal 0, we have the classical KdV, the classical KdV equation. Okay, so basically, the aim of this part of the talk is study trapped wave solution for the case in which the dynamic of the free surface is governed by the FKdV equation. Besides, we consider that the bottom, right, the topograph, is given as a sum of two Gaussians, which are distance, which are separate one of each other by a distance of 2 beta. And we also assume that in the initial wave is the classical KdV solution, is the classical solitary wave solution of the KdV equation. Okay, so this work is a numerical work. So basically, we need to solve this equation numerically, and the approach that we use in our study is the standard pseudo-spectral method that consists in basically we pass the Fourier transform in this system and obtain ODE in the Fourier space, and we solve this ODE. But we need to take care of some points. This ODE is a stiff problem, so in order to control the stiffness of the problem, we use a combination of integrate factor and Ruji-Kutta. So once that we solve this ODE in the Fourier space, we use the inverse of the Fourier transform and obtain our solution, the physical space. Okay. Just to let's remind some points here. Okay, we are dealing with a problem in which the free surface is given is the solution of this PDE, and the topograph is given by this equation here. And in order to carry out numerical simulations, we need to control 4 parameters here: f, which is the perturbation of the fluid number 1. Beta, which controls the distance between the bumps. A, capital A, which controls the amplitude of the initial wave, and the parameter epsilon, that controls the nonlinearity, the dispersive effects, and the topography at the same time, which appears here in the equation. Okay, so now I'm going to show you a simulation, an animation for the case in which the initial amplitude is 0.5 and the parameter epsilon is 0.001. So let's play this animation. So as we can see here, initially the wave, this solitary wave, let's say this, oscillate, right, between the bumps, between the bumps. Because of that, we say trap the wave. Observe that the wave is trapped between the bumps. But after some time, as we're gonna see now, I think, yeah, the wave escape out the region. So we are interested in investigate how this trapped wave solution behaves when we change the parameters. So the first study that I'm going to show is what happened when we change, when we vary the distance between the bumps, right? So what I'm showing here is the following. We are plot the time of escape, because as we saw previously, the wave oscillates between the bumps, then eventually it escapes. So we plot here the time of escape as a function of beta, the distance of the bumps. As we can see, this is basically a linear relation between time of escape of beta. What is at somehow expect this result here? But now let's see what, let me explain what I'm showing here. So basically, let's first fix our attention on the top here. So on the top, we see the momentum as a function of t, where t here is escalate, right? As it's shown here. We are seeing here the momentum for different choice of beta. So what we see from this figure is that the momentum oscillates, increasing until the wave overcomes the bump. At this and here in this figure now, I'm showing the height of the peak of the wave. So for different values of beta. So initially, as I mentioned, the wave had initially the initial amplitude of the wave was 0.5. Then when the wave reached the bump, it gains amplitude. Then when the wave reached the bump again, it lost amplitude and its amplitude keeps oscillating and increasing until the wave escapes out. Okay, so we see that the waves, that given a wave, eventually it escapes out. So the main question that arises is that what is the cause of the escape of the wave? In order to try to answer this question, we consider the following. So let me explain this figure here. It is a bit of hard to understand this figure. So here I'm plotting the peak of the momentum, P. We are plotting the peak of the momentum at each rebound. So, and each color here denotes a wave. For example, let's track this red circle here. This red dot here represents a wave that initially, in the first rebound 1, the peak of the moment was this value here. Then, in the second rebound, the wave gained momentum, And in the second rebound, the peak of the momentum is given here. And the third rebound, the peak of the momentum is here. So if we follow each rebound of the red wave, we see that when the wave crosses some level of the momentum, it escapes out. Basically, we conclude that there are an upper and a lower bound for the moment, that once the wave crosses this threshold, it escapes out. More than that, pay attention in this this gray wave here. So if we choose initially one certain wave whose momentum is below this bound, this lower bound, we see that this wave just pass over the bump without oscillating. Okay, now let's see what happens when we vary the amplitude of the initial wave. Okay, so let's first explain this figure here. This figure here is like a phase portrait for OD. So imagine that we are in the solution space. And in this solution space, we have two parameters here, the amplitude and the crest position, the crest of the wave. And as it's shown here, it's said here, the bumps are located at the position 20 and minus 20. So let's start here. Imagine, let's assume that we consider a wave that initially is located at this point, and whose amplitude is this one here. So what we see from this picture is the following: this wave will traveling, then when it reaches this bump here, it will just reverse its movement. So this kind of wave here we call repulsion waves. Now let's assume that we pick a wave that is here in this yellow line. So what happens here is the following: this wave that starts here will just pass over the bump that is located here in the position 20, then travels, pass over the next bump, and go and follow traveling. So this kind of wave we call passage waves. And what you see here is that there are some choice of amplitudes right here inside between minus 20 and 20, that if you choose a wave here, this wave will oscillate until escape. So, oops, sorry. Oops, something happened. Okay. This classification of the waves in passage, repulsion, and trapping was reported by Greenshaw in the study of trapped waves over one bump topography, right? Okay, now let's do the following. In all previous simulation, we used that epsilon was this value here. Now, let's change the value of epsilon and see how this variation will affect the flow. So remind that epsilon appears in this part of the equation here, controlling the forcing term. Okay, now I'm using epsilon equal 0.1. So let me play this simulation. This simulation, sorry, let me play the simulation. This simulation is a bit slow. So because of time, I will speed up for the important part. So basically what you see here is that the wave is just oscillating as before, but the novelty will appear at some point here. Okay. So this wave was oscillating. Then what we can see at this moment that some kind of resonant mechanism appear and the flow start to, oops, no, is now, sorry. Let's wait a bit more. Okay, it's now. So the flow will start to generate solitary waves that propagates upstream. And the flow keeps generate solitary waves as far as we let the simulation run. Right. So as I said, so in this, when we change epsilon, we see that somehow some kind of resonant mechanism arise in the flow. So just because of time, I will show this picture that is just the same simulation here, but given a different way. So basically, as we have just seen, the wave oscillate. Then at some point, at some time, some resonant mechanism arise, and the flow starts to generate solitary waves that propagate upstream. Okay. Now let's play a different game. Let's assume that between the bumps there are two waves. A wave zeta A, where A represents the amplitude of the wave, and another wave zeta B, and again B represents the amplitude of the wave. We are interested in understand what happened in this kind of configuration. Okay, basically, we want to understand how two waves dancing together between the bumps. In order to do that, we solve this equation, the FKdV equation, for three different initial data. First one, we consider as initial data just the wave zeta A. Then we consider as initial data just the wave zeta B. Then we consider as initial data the sum of the two waves. So let me explain this figure here. This figure here summarizes some certain experiment. So in this figure, we show the position of the crest for several times. So, for example, let's fix our attention in the red line. The red line denotes the solution for the solution for the case in which the initial data is just zeta A. So basically, what we see here. So if we track the red line, we see that this wave oscillates. Just track the red line. Oscillates among the bumps, because the bumps are located, one here in -20, another one in 20. Then eventually the wave escapes. The same goes to zeta B. And we see that the same goes when we take as initial data the sum of the two waves. The two waves interact with each other. This is, I'm following now the black lines, and after some time they escape out. So basically the dynamic is the same. But now let's see what happens if you choose another value for A and B. Okay, for this case here, if we carry out the simulation for just zeta A, red line, we see that this wave escape downstream or escape to the right, and the same goes to the wave zeta B, also escapes to the right. But when we plug together zeta A and zeta B and run the simulation, we see that the dynamic change completely. Now both waves escape to the left or escapes upstream. So at somehow one wave affects the other. So, but now let's give more details about this dance of the two waves. So when you have as initial data two waves, the sum of two waves, the sum of two waves, the dynamic can be classified as, first, can be classified in three events. Let's say this. First event, the two waves can escape upstream. The two waves can escape downstream, or the waves can escape in opposite direction. So basically, we have three events here. So when you have events, the question that automatically arises is, what is the probability of each event to happen? So in order to answer this question, you consider the following. We consider a certain set SA and a certain set SB, and each of the set they have more than 1,000 elements. We take the Cartesian of the set, and as this Cartesian is a big set, right? We take some subsets of this Cartesian, and we consider values of E and B in these subsets. So basically, you consider 4 subsets and compute the probability given by each one of the subsets. So basically, we see that the probability is almost the same for the 4 subsets. This shows that the number of elements considered for compute this probability, it's fine. So it shows us that, okay, we have considered enough elements in each subset. But the most important information given by this picture is the following, is this gray column here, or gray, sorry, is this gray column here. This gray column here represents the probability if the dynamic of the waves were independent one of each other. So basically, we see here that the probability, if you consider the probability of independent events, the probability is almost the same, which leads us to conclude that this kind of situation here, although you know that one wave affects the dynamic of the other, when you look this mechanism, this scenario, statistically, the dynamic of two waves are basically independent one of each other. And we also compute, just for give more details about the dynamic of the trapped waves. If we consider as initial data just Zeta A and just Zeta B, and take A and B in that sets that I mentioned before, and if you compute the percentage of the waves that escapes upstream or downstream, we see that the chance of a wave escapes upstream is much higher than the escape downstream. So this is somehow not natural. Let's say this. Okay, just some brief. Now I will give just some brief comments about the case in which we have a wave that remains trapped in a low pressure region. The results of this part are published in this paper here that I've made in collaboration with Marcelo Flammarion, who will speak today in this section. Okay, now the bottom of we consider the bottom as the bottom is flat, right? It's written here, the governing equations are the Euler equation as before, but they are written in terms of the potential, the velocity potential. F is the fluid number that represents the current. So in this part of the problem, we consider the full Euler equations and solve this problem. It's hard. I'm not explaining here the numerical method used here. I will just show two simulations for this case. Basically, we consider the pressure as it's shown here, right? So the pressure on the free surface, there is some area of lower pressure. And let me show the simulation. So basically what we see here, the dark blue area here indicates where the pressure is lower. And what we see is that we can find a trapped solitary wave solution for the full Euler. Here is full Euler equation, right? And now my last slide, just for fun. I love this simulation. Is what we see what happened when we put 3 solitary waves in the low pressure area, and as we can see here, they interact with each other. Then after some time, one escape, then they keep interact, then a second one will escape. And I promise that I'm about to finish. Okay, Adriana, because run of time. Okay, so my conclusions. So basically, from case 1, trapped waves for the FKDV, we showed numerically that trapped waves move back and forth, oscillate between 2 bumps until reaching a threshold of moment to escape out. Also, our experiments indicates that the trapped waves have a certain tendency to escape out upstream. This is very unnatural. We also showed that when 2 waves are considered between the bumps, one wave affects the other. However, this is important, when we look at the problem statistically, the waves behave as they were independently. And for the last part, we showed regimes in which there exists trapped wave solution for the full Euler equation. Okay, so that are the reference that I mentioned during this talk. The first and the second reference here are the work that were the base for this presentation, and here is the work of Grinshaw and Milevs that I mentioned. Okay, thank you for your attention. So I'm available for questions and comments.
Thank you, Roberto, very much.
Adriana, I think I passed 2 minutes of my time.
That's okay. We started late, so it's fine. Don't worry about it. I don't know if anyone has any questions. You can open your mic or maybe do it through the chat.
Hi, Roberto. I have a question.
Okay, yes, please.
Yeah, yes, thank you for a very interesting talk. Can I ask about the importance of the current term? So I notice you've scaled it so your Froude number is close to 1, but how much does varying the current change the picture that you've been showing us?
Okay, thank you, Rafael. This is a very good question. Thank you, Rafael. Okay, let's basically, just to give a very quickly answer, let me show this case here. Okay, let's go to FKDV. If we don't have a current, basically we don't have trapped waves. That is one way to answer your question. But another way to answer your question is the following. We can imagine that instead of have a current, we can imagine that this topography is traveling with this speed here. I don't know if I answer your question. Basically, I'm saying that okay, I can drop this hypothesis of current, but if I drop this hypothesis, I have to assume that the topography travels with the same speed of this current. So basically, we basically change the hypothesis of having a current for having a traveling topography, basically.
So can I maybe I can rephrase that. So I understand that without a current, there is no wave trapping in this scenario. Okay. And it seems to me, because I noticed in the simulations, there's some energy radiating away, right?
Yeah, okay.
Yes. And so is it correct to think about the problem as if the solitons are taking energy from the current, right? You start off with your set squared, and it's bouncing back and forth. But why can the amplitude of the soliton increase here? Is it because it's taking some energy from the current?
I saw your question. To be honest, I don't know, but I understand your question. I understand it very well. I don't know, because as you can see, when we monitoring the momentum, right, we see that the momentum increasing. my idea is that this increase of momentum is because some nonlinearity that comes from the forcing term. But I'm not able to prove this, right, Rafael? But understand your question now.
Okay, thank you. It's very interesting work.
No,
so thank you
available.
again.
If you want to have a chat about this, I'm available. You can have a chat another opportunity.
Thanks.
Okay, thank you, Roberto. Another question? I don't see anything in the chat. So if not, let's thank Roberto again. Thanks for being here.
Okay,
and
so just my last comment, right, Adriano? My last comment.
That's okay.
I do apologize with the next speakers because I cannot stay for this section because I have to travel. I'm going to drive now for 10 hours.
Oh my God.
So I do apologize with the next speaker. I would like to stay, but I can't. So I'm sorry for this, guys.
So have a nice travel.
Bye-bye.
Bye. So next talk is programmed to be at 10 a.m. So we have a little coffee break and we will come back shortly. Thank